Thank you. I'm Mathias, and this is Lucy. We are both engineers in the Uber Aarhus office, and we're sort of put together. We like big numbers, so we called it migrating 2 million containers to cores to Kubernetes, because that's basically what we've been up to for the last year or so, at least some of us, yeah. So we hope this can serve as an example of what it takes to adopt Kubernetes into a big organization, big IT tech company like Uber. So the first question I expect that everyone is going to have when sitting in this audience is, how on earth does Uber use 2 million CPU cores? Isn't it just this ride-share service that existed for a short while back in Copenhagen in the mid 2010s? And yes, it is, but it's also a very big global company. We are live in about 70 different countries across the world, basically, but unfortunately not in Denmark yet. We have two major products that we sell on our platform. Both are on-demand products. The first one is what I have a picture of here, which is our ride-share product. That's basically on-demand. You get from somewhere in a city to another place in a city using our on-demand ride-share service. The other one is food delivery on demand. So you basically order food and you get it to your doorstep. That's something that we have competitors that do it in Denmark as well, of course. In combination, and the reason why the platform is as big as it is that combined these two products, we have about 23 million transactions every single day. 23 million times per day, someone either takes an Uber ride or orders some food on our platform. And that just adds up to everything needing to be big. That's almost 1 million transactions per hour, and they take a while to complete, right? So there's always a lot of stuff going on this platform. Second question is probably Uber in Aarhus. I've never heard of that. And we have at least for Aarhus, a fairly large engineering presence in downtown Aarhus. About 120 engineers working mostly on infrastructure for Uber, so the platforms that power all of the Uber products. I'd be happy to talk much more about that, but this talk is going to be mostly about technical stuff, so just skip ahead and talk about our Stateless Platform. Our Stateless Platform is the platform where we deploy all of the back-end business logic of Uber. So that is, whenever you make a change to your code, you go to up, or automatically it deploys your change through this up system. At Uber, we have about 4,500 microservices that are deployed into our production system, just one big production system. They are, of course, deployed in multiple instances, multiple copies, each of them. And that adds up to about 2.8 million cores of stateless microservices running in our data centers across the world. We migrated almost. We were hoping that we had gotten to 2 million by this talk. We're almost there, right, Lucy?
Yeah, we're at 1.85 million.
1.85 million as of yesterday. But I think we did 150,000 cores yesterday.
Yes,
so
exactly.
If we had done this talk tomorrow, we might have been there. But that's anyway. We believe very strongly in continuous deploy at Uber, which means that we deploy about 31,000 times to production every single week. So there's like a lot of changes going out to production all the time. We have a few dozen clusters backing this system. Lucy's going to talk much more to that later, exactly what that topology looks like. Then finally, I've included a graph just for clarity, or lack of clarity, of all our microservices. The dots are the services. The edges between them are the call edges, RPC call edges. So it's like a very tightly knit, very closely coupled system of more than 4,000 microservices. And we deploy that on this platform. So how do we make that work in practice? How do we actually make something like that as complex as that scale to a large size? What we did in Uber Aarhus is we built this system called Up, and Up attempts to abstract away most of the infrastructure concerns that engineers have when they deploy stuff and when they use these cluster systems. So Kubernetes, for example, is great for most engineers. When we scale it up, you have to sort of have some aura in how people are using it. So when most of our engineers deploy or set up their services on this platform, all they do is that they say sort of roughly how many instances copies of the service do they need in each of our regions. and sort of roughly what is the configuration, what is the Docker image that they want to deploy, and what are the dependencies, sort of high level of the service. And then Up is responsible for taking that very high level description of the service and then continuously applying that to the clusters below. There's a fairly complex compiler that we won't talk much about today, but that compiler takes that high level configuration and generates Kubernetes specs and generates specs for the other cluster systems that we have on this Up platform. It continuously optimizes placement, etc. For these services. Oops. So I'm gonna.
Oh, do you need my touch? Do you need my touch ID?
Oh, sorry.
Live demos.
Live demos. I wanted to give a quick live demo of what this system looks like.
Yep. You have to use the mouse on here to go on that screen.
That's fine. It's just going to be
you're going to have to look up there.
30-second demo here. That's the reason why we had to use our own laptop here, because we wanted to have live access to our production system just to brag a bit about how things work. Right?
Yeah, we're going to crash the Uber app live right now.
So we built this Up system that runs on top of Kubernetes, and when an engineer wants to deploy something on this platform, all they do is they go to this UI, they click deploy, they pick whatever whatever they want to deploy. I'm just going to deploy the latest thing of this, the latest commit to master of this test service. And then they can choose between a couple of different policies to use for applying that to production. And there's a bug right there, but I think it works anyway. Let me just,
it does. It just takes a few seconds.
It takes a few seconds. There is.
There you go.
So now the compiler ran. It generated specs for Kubernetes. It starts applying it one by one to the clusters across the different zones, across the various regions that this thing is deployed into. What you can see here is that in this particular case, the platform decided to go to 3 different availability zones, and now it starts putting new versions of the containers into the Kubernetes clusters while it's monitoring and sort of slowly applying the change as it progresses, making sure that we don't break all of the Uber platform, all of Uber's products at the same time. So if you apply slowly, at least some of the things haven't been broken yet if you apply them like one by one in terms of zones, right? So that's how it works and what it looks like to our engineers. So let's take a look at let's take a look at the.
That's fine. We've got 41 minutes.
We got 41 minutes. Thank you, Uber security. I'm gonna hit start slides again here. All right. And that was our backup thing. There it is. All right, so when we built this system originally, we did consider Kubernetes, but at the time Kubernetes was not very mature. You could find some super interesting blog posts about how some folks have been able to scale Kubernetes to about 1,000 hosts in production, and we were like, whoa, that's on one side that's impressive how many hacks you had to make to make that happen, but on the other side, we're going to need 10,000. So probably Kubernetes isn't quite ready. That was back in 2016, 17, I believe. So we started initially by using an older cluster management system called Mesas for backing our system. But then a couple of years ago, we went back and sort of reevaluated. We could see that Kubernetes had gained a lot of traction, and that was basically where all the focus was of the community. It had become the standard across small and medium-sized businesses, and we could see that at about 50% of the Fortune 500 companies in the US had adopted Kubernetes as their container orchestration platform. We could also see that the system we were using, Mesas, was getting less and less attention from its owners, from its committers at Apache. So we decided that we had to do something. We had to modernize this system. We could also see a future opportunity to consolidate some of our other platforms. So we also have a platform that we also built in Aarhus for stateful databases. That's another couple of million cores. There's a platform for running machine learning and for running offline batch jobs that do, say, payouts and tax calculations, all these things that happen. So there's a bunch of other platforms here that in the future could also work on Kubernetes. We also had to make sure that when we did this migration, there had to be no impact on our product engineers. So they had to be able to just keep building and working with the system the same way that they've done so far without any disruption from this migration. It had to be transparent, so we couldn't have any downtime. As you can imagine, if you do 1 million transactions per hour, downtime pretty quickly adds up in terms of revenue. So we didn't want any of that at all. We wanted to retain the federation layer that I just showed you, so we could keep all all of our safety and compliance, etc., stuff that we already had in this layer. So we sat down and sort of thought about what would it take to actually migrate live a system of 2.8, initially 2 million containers to Kubernetes without breaking anything, without letting anyone know, really. We came up with a concept that we call portability. And portability at Uber is essentially about decoupling the services from the underlying infrastructure, both the physical infrastructure, the topology of that infrastructure, as well as the container orchestration platform, the scheduling software, if you want. We wanted this property to ensure that we could do a touchless migration where we wouldn't have to involve anyone, but the infrastructure engineers. And we needed it to ensure that we had zero downtime as we migrated between clusters. And we wanted to make sure that since this is an investment, this was an investment to introduce this portability contract between the platform and the services, we also had to be able to reuse it over time, meaning that the next migration should also be able to build on portability. So it couldn't just be a bespoke thing for just this migration. Just to give an example of a couple of other migrations that we are crazy enough to do alongside the Kubernetes migration, we are migrating all of our data centers. We're migrating all of our capacity essentially to cloud on Oracle Cloud. And at the same time, we're also migrating much of it to ARM hosts. So if you want to run 3 of these migrations on top of each other, it sort of has to be automated, and you have to have some foundations that works. So in portability had 2 sides when we introduced that. It had what we call movement tolerance. So the ability for us to take a service or a replica set, if you want, in Kubernetes, and then move that as a whole from one cluster to another one, either in the same availability zone or in a different availability zone. That was something that the services would then have to support without behaving differently in this other cluster on this other zone, and the infrastructure below it would be able to perform this migration, this movement of the service without breaking anything, without breaking any SLAs. The other part of it was what we call distributability. So the ability to take a service or a replica set, if you want, and split it into 2, and then deploy these 2 parts of it in different places, potentially different zones, but definitely different clusters. These 2 things combined make us able to move all of our capacity, split it up, move it between clusters, move it into Kubernetes, move it out of Kubernetes if we saw any issues in the migration, so that it could just be a complete non-event for everyone that wasn't in the group performing this migration. So with that product and with the portability work done, so that we had a clear contract, I'll let Lucy talk to how we did the actual migration and what our Kubernetes setup looks like.
Awesome. Thank you, Mathias. So our Kubernetes fleet sort of looks like this. We have divided into multiple regions, and within those regions we have these availability zones. The vast majority of our compute is in the US, but there's some points of presence in countries like Korea, where local laws mean we have to process data in the country. Previously, before our migration, all of this would have been Peloton clusters, which is our compute orchestrator that ran on top of Mesos. But mid-migration right now, we have a mix of Kubernetes and Peloton clusters. Some zones may only have Peloton, some may only have Kubernetes, some may have both. The up backend before we moved to Kubernetes turned the state that it wanted to apply into Peloton. It was stored in this generic state and then turned into a Peloton command to run. We ended up slotting in there our new backend for Kubernetes so that we could have both running in parallel. So we have this generic goal state object in side up, and then depending on what backend the command is going to, it will either get turned into Peloton commands or Kubernetes commands. This is what we call compiled. So some of the challenges we've had with Kubernetes is not exactly the same as Peloton. So we've had quite a few, but I've only really got time to talk about 3. So Reperformance, controlling our rate of change, and debugging with snapshots. So first off, Reperformance. The requests that our engineers make to up are normally quite wide-reaching. They may, for example, if they go to look at a service on the UI, we need to find all of the different pods where that service is running across all of our clusters. So that means sending a list request to all of our clusters. We worked out very quickly that this was going to stress the underlying etcd nodes in Kubernetes so much that they were going to blow up the control plane. So we can't do that. We got to do something different. What we ended up doing is we built this in-memory data store inside up. We have watchers listening to all of our clusters across all of our fleet. And these watchers then push data into this data store. We index it there, so we'll index it by service, for example, and important attributes like that. And then we serve that data, and then we use that data to serve users when they ask to see the state of the system. Our NTP, our network time protocol synchronization is pretty good. So to make sure data is fresh, most users can ask us like, hey, I want to see data that is at least after this time, typically now. And then that's how they make sure they don't get data that's really stale. So that's how we solve for that. Yes, controlling rates of change. So, as Matthias mentioned earlier, in our system, we don't want changes to apply everywhere immediately because we want to watch the progression of this change, watch our alerts, watch our monitoring, and if we see a problem, we can automatically roll back to the previous state, which we hope is safe. Normally it is. So obviously in Kubernetes, when you apply a state, the Kubernetes will obsessively try to get there as quick as it can and apply it as fast as it can. We didn't want this to happen per se. We wanted to control this. There's also some programs that actually don't like being disrupted that much. So, as Matthias showed earlier, we have this plan system. So when you ask up to change your service, up looks at the current state of your service and it looks at where it should be, and it produces this plan. This plan is then broken down into these series of steps that are up here. Each step is like change a certain number of pods or containers for the service across one of our clusters. And each one can have a waiting period during which it looks at monitoring and other health checks to make sure that the planned step applies successfully. If it doesn't apply successfully, you get into a rollback. And when it rolls back, it just takes the previous state of the system, applies that to all of the clusters where it's changed things. And then by doing so, we hopefully bring the service back into a safe state. Most of the time that works. Otherwise, service owners got to go do something themselves. So that's how we solve for that. And yes, container snapshotting. So inside Uber, engineers are quite familiar with debugging their containers by getting a snapshot of the container at the time it exited. This is very common inside Uber. Because it was very common when we were using Peloton, and this was very much a blocker. Like, engineers would be very angry at us if we took this off them. Inside Peloton, this is quite easy. Peloton doesn't clean up container artifacts after your container exits, so we just give them a link to the container artifact, and they can go get it, and they're all good. In Kubernetes, not so much. In Kubernetes, it's much more diligent at cleaning up after itself, so the container artifact gets deleted very quickly afterwards. So we had to come in here and change this too. What we ended up doing is we built our own artifact uploader that uploads into a blob store that we have called TerraBlob. So the way that works is we have a sidecar container running against all of our services pods. It's waiting to see the pod is exiting. Once it sees the pod starts exiting, it stops it from being deleted. It takes the volumes and the snapshot data, uploads it to TerraBlob, and then once that's done, it will then let the container gracefully shut down, and then it gets deleted like normal. That then goes into the up UI, and from the up UI, people can click on it and access TerraBlob, and they can see their container file there, and they can have all of their nice debugging needs. So, oh yes, and with all of that and a few other things, we should be able to see.
I probably shouldn't touch it, yeah.
You're not going to touch it, okay. Yeah, I can't blame you. So let's see if this opens. Yeah, it does, okay. With all of this and a few other hacks, we should be able to see that the rollout we started earlier in this presentation on Kubernetes is, this is actually a UI bug. It's, there we go.
It's eventually complete.
Yeah, eventually consistent.
Yeah.
Has succeeded on Kubernetes. Awesome. Right, let's go back to the slideshow. Cool. So, what we've learned thus far with our journey on Kubernetes. Kubernetes is not a magic bullet. It's not something that we just slotted into our infrastructure and we just threw our services on it and then we never had to think about them ever again. It's not the be-all, end-all of our systems by default. And it didn't make us all unemployed, luckily. But the flexibility of Kubernetes is its strength to us. It's the fact that we could change the behaviors as much as we did to make it work with our services, and also to make it feel like engineers almost a bit like Peloton, so that from a portability perspective, we could get them onto Kubernetes, made it really powerful to us. And that flexibility is really the most powerful thing, at least to us, about Kubernetes. So on a migration, the first million calls were the easiest. Most of our services, rather non-opinionated, rather not many dependencies on the underlying systems. Moving about 80% of them took maybe 20% of the work. And then we had this long tail on the rest of them. And that's because we've learned very much that any behaviors we expose to our end users will get built on, documented or not. We found some quite weird and wonderful behaviors that engineers have built. Some of them built even looking at compute host names to do something. I can't even remember at this point. It was pretty insane. But yeah, our migrations like this are definitely things that have a long tail to them. But we've learned from that. And one of the nice things we found about our migration is that running both Peloton and Kubernetes next to each other at the same time meant we could onboard people to Peloton and very quickly bring them back off onto Kubernetes. So this wasn't something where you moved to Kubernetes and you just had to hope you worked. And if you didn't, you're screwed. That de-risked this a lot. So our current migration state, I think we mentioned earlier, this graph is actually a bit out of date because it changed overnight, basically. Yesterday, it was 1.74 million CPU cores moved, and I woke up today and it's 1.85. So we're getting there. Our biggest clusters now have got about 5,500 nodes. Probably a good idea that we don't push it too far because we've heard about the horrors that Alibaba had at 10,000 nodes. So we'll probably just add more clusters from this point forward. Hoping to have 2.7 million cores all moved and all done by the end of the year. See how that goes. Come talk to me in a few months and you'll find out. And after this, we're going to keep going. So this solves our stateless compute needs, but we have loads more. We have Stateful, which has, I think, even more CPU cores than stateless at this point, does it?
Yeah, it's a little less, but it's more than 2 million.
Yeah, it's more than 2 million.
It's still a meaningful.
Yeah, so we haven't even migrated those yet, or batch workloads and things. Those we're hoping to bring onto a common platform built on top of Kubernetes over the next few years. It's going to be a very, very, very big move of a lot of stuff. It's going to be, what, another 4 million plus, you think?
Yeah,
yes,
something like that, yeah.
4, 6 million, yeah. Thank you for listening. We are going to be here all day if you want to ask any questions. There's also a load of other people from Uber over in this area. I'm sure they'll move at some point. If you want to read more, there's a blog post which we didn't actually put a link to that you can click, so that's our fault. Hey, eventually you'll get the slides and then you'll be good, okay? But yeah, thank you very much for listening, and see?
Thank you.
Oh, thank you.